Hemophobia is the debilitating fear of blood. If you hope to watch this video all the way to the end, then I'm sure this phobia doesn't apply to you. If it does, well, you read the title of the video, right? We're talking about blood. All kinds of blood. Red blood, blue blood, yellow blood, clear blood. We're gonna dive into it. Well, not literally, that's pretty gross. There are so many different colors of blood, and we're gonna talk about each one, try to pick which one is best, and be sure to stick around to the end where I'm gonna do a little bit of myth busting. Then, you will know more than could possibly ever be necessary to know about blood. Blood is important to us and many other animals, as anyone could assume, because without it, there's not really an alternative. Blood does a lot of things. It carries nutrients throughout the body to make sure you have energy. It carries hormones throughout the body to make sure that you're functioning properly. It facilitates waste removal, and it helps your immune system move around your body at super speeds to cure infections. But most importantly, your blood transports oxygen. When you take a nice deep breath, which is actually a little difficult for me right now. Sorry. When you take a nice deep breath, the oxygen in the air that you just breathed in binds to the hemoglobin in your blood that's in the capillaries in your lungs. Hemoglobin is a protein that your body produces to transport oxygen throughout the body. It uses iron as its active ingredient to bind to the oxygen. Your body has a lot of hemoglobin in it, with about 25 million per red blood cell in your body. There is so much hemoglobin in you that it actually changes the color of your blood. When the iron in the hemoglobin binds to the oxygen, it creates a bright red color, similar to why things turn red when they rust. There's so much hemoglobin that it actually affects things more than just what you see. You can also taste and smell the iron in blood. Iron does a...
Let go of my man bun?
Sweet baby. His name is Wellingsworth. Sir Wellingsworth, actually.
You keep distracting me.
Iron does a fantastic job at binding to the oxygen that we breathe in, but what about other elements? Well, I'm sure by reading the title of this video, you know that the red color produced by hemoglobin can be other colors produced by other molecules. There are skinks in Papua New Guinea with lime green blood. Blue blood can be found in animals like squids, crustaceans, spiders, snails, horseshoe crabs, and of course there are exceptions to some of those depending on the species, but the peanut worm has clear blood until it's oxygenated, in which case it turns purple. The ice fish has always clear blood. Starfish, using their primitive heart, actually pump water through their body rather than blood. And animals like jellyfish have just completely ditched a circulatory system to begin with. Okay, that was a lot, but don't worry, we're going to break it down each one at a time, going in order from most similar to us to weirder and weirder as we go on. Starting with Brazinohemavirans, the green-blooded skinks I mentioned earlier. Their green blood actually changes the color of their muscles and even bones, but the reasons for their green blood is, in my opinion, much cooler than the results of their green blood. Basically, when your body breaks down old red blood cells to be excreted, yes, by the way, your poop is brown because of your blood, and your pee is yellow because of your blood, but anyways, that's besides the point. During the process of breaking down those old cells, a byproduct is produced called bilirubin. It's a bunch of complicated organic chemistry, but the bilirubin that would normally be excreted in a human body is allowed to accumulate in the skink's body and turn into something called biliverdin. This may seem dangerous, and to a human, it's very dangerous. Actually, the skinks allow the biliverdin to accumulate to 40 times the lethal limit for a human. This high concentration changes the color of their blood, but that's not like why they did that. They do it because it acts as sort of a shield against malaria parasites. And since the skinks live in an area where malaria is such a huge risk, this adaptation is really important to them. This green-blooded trait has actually evolved among several other species of animals in the region, meaning that this isn't just a fluke, and it does actually work and is serving its purpose. And this is an example of convergent evolution, which of course you would know if you watched my carcinization video, which I'm sure you have, right? Anyways, scientists are trying to isolate the gene that the skinks use to be immune to such high levels of biliverdin and see if we can use that for helping humans in regions where malaria is dangerous. Okay, next, and equally as interesting, yellow blood. This type is mostly found in sea cucumbers and some tunicates. They still have hemoglobin like us and the skinks, and some of them also have hemocyanin, which I'll get to later. But they also have a protein called hemovanadin, which is not used for carrying oxygen. Hemovanadin uses vanadium, which is a metal that our body requires to function properly, and of course in concentrations large enough are fatal to us. But not to sea cucumbers, because they can accumulate 10 million times the concentration of vanadium as the surrounding seawater. The reason for having so much of this vanadin in their blood is still kind of unknown, but there are some pretty good theories. The best theory, in my opinion, is that the high concentrations of vanadium make them toxic to predators. It was thought at first that hemovanadin was used as an oxygen-carrying protein like hemoglobin, but it already has hemoglobin or hemocyanin in its blood, which are oxygen-carrying proteins, so why would it have both? It doesn't make sense. Alright, but next up is purple blood. Animals like the peanut worm and some other weird worms use a protein called hemerythrin rather than hemoglobin to transport their oxygen. Hemerythrin is actually pretty similar to hemoglobin as well, as it still uses iron as its active ingredient, but instead of 4 iron ions, it uses 2. Moving on though, what's this hemocyanin I keep mentioning? Let's ask Lady Liberty. The Statue of Liberty is a 151-foot tall statue gifted to the US by France in the 1880s as a gift, a sign of friendship. You may already know this, but the statue is made out of copper, and its blue-green color actually comes from the copper oxidizing over time. It used to be brown, and now it's the blue-green color. This can also be seen with old pennies. Hemocyanin is the copper version of hemoglobin. It uses copper as its main ions. Hemocyanin produces a stunning blue color when it binds to oxygen, and it's actually free-floating in the bloodstream, meaning it doesn't have to hitch a ride on a red blood cell like hemoglobin does. This has its own benefits, but we'll get to that later. Hemocyanin is the second most common blood type in the animal kingdom, with hemoglobin being first. But what I find interesting though is that hemocyanin evolved 750 million years ago, which is 300 millions sooner than hemoglobin did. Hemocyanin is way more ancient than hemoglobin is by 300 million years. Which I think is so cool because when we think of blood, we think of a red color, an irony taste, but really, that's not the original blood. The original blood was blue and doesn't taste like iron. I don't know what copper tastes like actually. And the last color for this video anyway is actually not a color, clear blood. This can be found in ice fish and other fish that are members of the family, let me check my notes. Chinichthyeidae, first snake. These little guys live in the Southern Ocean near the Antarctic, so their water is pretty cold. And a fun fact about cold water is it's able to hold oxygen way more effectively than warm water. So the water where these fish live is actually very oxygen rich. You know that these fish used to have hemoglobin by looking at their genes. They still have the genetics for producing hemoglobin, but they don't produce hemoglobin, nor hemocyanin, or hemerythrin, or any of the others. They don't have any of those molecules. This is nice for saving energy because it's less energy being diverted towards producing those proteins, but it does come at a cost. This does result in a slower metabolism, wider blood vessels, greater blood volume, and spongy heart muscles, which is actually pretty interesting because this means that the heart doesn't have to worry about making coronary arteries, which are the arteries that feed the heart oxygen. So it does save them some energy because they don't have to produce those proteins, but overall they are less efficient creatures, despite their adaptations actually being really fascinating. Okay, that was a basic overview of all the colors of blood. But why are there so many? I mean, which one is best? There's gotta be a winner, right? Well, that's actually kind of disappointing because in most things in science, there isn't a clear answer. It always just depends. So there is definitely a clear loser, but there's not really a clear winner. For example, hemocyanin doesn't have to be carried around in these big old clunky red blood cells, and they can weasel into every little nook and cranny of the circulatory system, making them more efficient for places that are cold or low in oxygen, like where the octopus lives, who has hemocyanin. To an octopus, hemoglobin would be a downgrade, but to us, hemocyanin would be a downgrade, because hemoglobin performs well in oxygen-rich environments. Every animal adapts to its needs in the environment and evolves the perfect traits to be as optimized as possible in their environment. I just said the same thing twice. Who wrote this script? While having blood with absolutely no hemoglobin would be unequivocally deadly to you and I, it's a perfect deal for ice fish. Hemerythrin may be 4 times less efficient than hemoglobin, but to peanut worms and its other weird wormy buddies, it's perfect. Hemoglobin is perfect for us because we're resource-intensive creatures. We aren't exactly sessile worms living in holes in the bottom of the ocean. We're running around and we're warm-blooded and we have these needy muscles that require so much energy and oxygen. Plus, we live in an environment with plenty of oxygen. Why not take advantage of that? We need hemoglobin to take in the oxygen to sustain ourselves. So, yes, technically there isn't a real winner or loser because it all just depends on the animal. But between you and me, it's hemoglobin. I'm definitely team hemoglobin here. Team hemoglobin. I think there's an important takeaway from this video though, more important than any of the information I just gave you, and it is that we are so inseparable from this universe, that the very aspect of our existence can be related to the cosmos. Our blood is red for the exact same reason that the surface of Mars is red, and for the same reason that the red sand beaches in Hawaii are red, and the same reason that some kelp forests are red, and that redwoods are red, and that garnet deep in the Earth's crust is red. We are red for the same reasons that so many other things in our universe are red. And I think that's beautiful. Even the little dudes with blue blood can be related to the universe as well. Those who have hemocyanin share their blue blood with the copper canyons in Mexico, or even the very water they live in, if they live in special places like the Blue Hole in Belize, where there are copper ions in the water. So basically, no matter how hard we try, we are entirely irremovable from this earth. We are only borrowing and exchanging the atoms we are made up of in the beautiful, interdependent economy of this planet. Okay, that got deep, but I did promise a myth bust here at the end. Look at my arm. The veins here are blue, even though I have red hemoglobin in my blood. It's a common belief that our blood turns blue and it's deoxygenated, and that's why our veins look blue. And I actually had a 4th grade teacher tell me that as an answer to my question when I asked why our veins were blue, which just makes me mad because no. Your blood can be varying shades of red, but it will never be blue. The reason our veins appear blue to our eyes is because red light penetrates easier into our skin than blue light does, and since blue light can't go as deep, it's reflected back to our eyeballs, and that's why we see blue in our veins. The blood is still red, it's just an illusion. That myth may be just a little bit unrelated to the topic of this video, but I'm still mad at you, Miss Johnson.